Hello everyone, today we are going to take a break from daily news and current events and instead going to talk about something slightly more theoretical. There may or may not be a Falcon Heavy test firing tomorrow. Apart from that, there is not really much changing. I will report about further updates as they come along, and I will talk more about the Falcon Heavy before it launches in early February. But for now, we're going to talk about rocket optimization in general and in theory, and today I will give you a quick introduction into the pros and cons of making a rocket tall and thin versus relatively short and thick, which would both encompass the same volume and thus allow for the same amount of fuel and a similarly purpose rocket design. However, both comes with actually surprisingly many different advantages and disadvantages, and so I will just purely theoretically talk about a few of these in a bit more detail so you can get a bit of an idea as to why certain rocket types might be so incredibly tall and thin while others look much more square, basically. Now, the most obvious considerations are, of course, aerodynamics and structure. Whereas the aerodynamic side would prefer a very tall, very thin rocket, keeping the cross-section as small as possible compared to the mass, reducing the aerodynamic force to mass ratio or the aerodynamic acceleration, thus the impact aerodynamic drag has on the overall launch trajectory and layout, and thus saving precious fuel and delta V, as you need less thrust to just punch through the lowest level of the atmosphere and need less altitude before you can start turning sideways and accelerating without worrying too much about aerodynamic drag just slowing you back down. On the structural side, however, you would prefer your rocket to be relatively short and have a relatively large diameter. This basically comes down to two factors. One is just a specific strength of materials and the square cube law, implying that if you build a vehicle to be larger in length or wingspan, in case of an airplane for example, you will need to use a higher percentage of the vehicle's overall take-off mass in structural mass just to support its own weight. The larger a rocket gets, and in case of a rocket that usually means the taller a rocket gets, the more percentage of its lift-off mass will have to be structural mass, and of course this makes the overall rocket design inefficient. This is also what somewhat limits how large you can build certain vehicles. Of course, the actual specific strength of modern materials is actually quite high, so we can build relatively large objects or structures, but for most vehicles we want the structural mass to only make up a small percentage of the overall mass, as we also need engines and fuel and payload and so on, and then there are also geometric factors, and so even with modern technology and materials, building a flying machine much larger than 100 meters would be completely unreasonable, as you would waste a lot of weight and mass into structural mass just to keep it all together, unless of course the whole thing is parallelized like a distributed mass flying wing or something like that. But for a rocket you usually have the engines on one end and then the mass distributed pretty much evenly throughout the length of the rocket, so you will have to structurally carry most of the thrust throughout the entire length of the rocket. Speaking of geometric factors, of course, there is also the ratio between a rocket's height and diameter, which essentially can be seen as a sort of lever. And if you just think about very thin, long struts, they tend to bend and snap rather easily. And while rockets are, for once because of this, designed to have most of their force just vertically exerted through the engines upwards and not bending it, some bending forces can't really be prevented, like certain aerodynamic forces, and of course the entire engine gimbal and attitude control issue. And so very tall and thin rockets have a tendency to basically snap in the middle, which has to be prevented by basically adding more structural reinforcements, which end up being unnecessarily heavy. This gets even worse as this geometric factor also adds elasticity essentially. The rocket not only has a tendency to snap in the middle, it also has a tendency to bend and bend back and forth, which can lead to unstable control states. We all know that from Kerbal Space Program, and of course that's not a perfect analog for the real world. There are some tricks you can do in the real world to prevent this, which Kerbal Space Program just doesn't offer. At the same time, there are additional factors and issues in the real world, but just to make it easier to explain, we all have suffered that problem in Kerbal Space Program where we had a rocket with the control core or probe core or capsule or whatever we were controlling it from at the top, and the attitude control being achieved through engine gimbal from the bottom. And if that rocket was too tall and perhaps somewhat aerodynamically unstable, it would start swinging back and forth, and as the rocket slightly bends, the control core is in a different attitude than the overall average of the rocket, and so the corrections that are being done aren't exactly correct for the overall state of the rocket. At the same time, any control output from the engines would first start bending the rockets and then only with some delay actually turn the entire rocket. And this would lead to some delay and some incorrectness in the feedback loop that is a rocket autopilot. And even if that autopilot is designed to handle this, any additional factors involved might still lead to some really dangerous states where the rocket is essentially bending back and forth and as a result either veering off path or just snapping in the middle. So between these factors there is a somewhat optimal height for a rocket that you try to reach, and if your rocket is relatively small you'll build it relatively tall and thin to not quite reach that height, as it might get too tall and thin and get into these bending issues, but somewhat taller and thinner than other designs, while a relatively large rocket might just increase the diameter to still fit into that optimal height. So the geometry of a rocket does somewhat just depend on its overall mass, payload and volume. However, the actual technologies used also have some influence on the design optimization, like the types of rocket fuels that are burned and the impact this has on the type of engines and fuel tanks used, as well as the materials and the state of technology. For one example, the material that pressurized tanks are built out of have a huge impact on their optimal shape. How important exactly pressure tank optimization is depends on the fuels used. Usually, for example, hydrogen and oxygen powered rockets need very well designed pressure tanks, while methalox engines can get away with somewhat less optimized pressure tanks and focus their overall design optimization on other priorities, but they still need pressure tanks, just not as extremely well optimized as for a LH2 LOX rocket. And here the optimal shape really depends on the material. From a purely geometric structural standpoint, the optimal pressure tank is spherical. That just gets away with the least amount of material and the least amount of structure needed to bear the pressure inside relative to the volume and pressure. So for any pressurized gas tank, a spherical shape gives you the best ratio of amount of gas stored in that gas tank compared to the mass of material you need to safely contain that pressure. However, with modern materials like carbon fiber enhanced plastics, this gets a bit more complicated, as these are, as their name says, they're fiber enhanced. So they're not actually the same strength in every direction. They are really, really strong along the fibers and really, really weak if you pull each fiber apart from each other. There are, of course, ways to accommodate more complex types of structures with carbon fiber compounds. You can use several layers of fibers laid in several different directions, But in the end, the most optimal way to use carbon fiber compounds is to build them into structures that are, for the most part, loaded in just one direction. So if you're building your pressure tanks from carbon fiber compounds, a cylindrical shape with spherical end caps that are a bit less optimized, but most of the structure and most of the relevant optimization taking place in the cylindrical part is more optimal than a spherical shape. And of course, the less optimized end caps get less relevant compared to the well-optimized cylindrical part, the longer and thinner that cylindrical tank with spherical end caps is. And so a carbon fiber compound tank is most optimal when it is really long and thin, while a non-fiber compound tank from any metal is most optimal when it is spherical. There are, of course, a few other issues about carbon fiber tanks that I might talk about in a separate video, but for now that's really all we need to know about them. They are really strong lightweight materials, and so they're still worth using, but they mean that you have to optimize your design differently, but of course still taking all factors into account, not just the fuel tanks. Another point of optimization is of course based on the engines, and these don't really seem to depend too much on the rocket's overall shape, but there is still some minor factor to be considered, as it is most optimal for your rocket engines to cover most of the rocket's base. Having a really lightweight rocket with a huge diameter but only tiny engines on the bottom is possible, but it's not really aerodynamically optimal, and given that most rocket engines have a somewhat similar specific impulse and depending on fuel type a somewhat similar fuel density and based on their specific impulse also a similar exhaust velocity, which is essentially the same as specific impulse with a minor deviation based on trigonometry, there is, depending on what type of fuel you use, a fixed optimal ratio of thrust to engine nozzle area, at least for the first stage, which should be optimized for sea level pressure. And of course that thrust to area ratio combined with the density of your rocket fuel and an optimal thrust to weight ratio for a rocket gives you again a somewhat optimal height for your rocket. Now depending on design there might be vastly more complicated factors impacting this later on in the design, but for a first overview these are the most important factors that determine how a rocket looks geometrically. I might go further into this later, but for now this is my introduction into rocket height and geometry optimization. I am of course always open for any questions about spaceflight or physics, if I can find the time to answer them, and as always, thanks for watching.